Okay, so today, derivatives of exponentials and inverse trig functions. So first of all, we're going to talk just basically about our exponential function rule. Okay, and this is basically if you have some value b, let's say 2. So if we were asked to take the derivative of 2 to the x, meaning my exponent is a variable x, the derivative is just that base b to the x power times the natural log of whatever the base is. Okay, so this is one that essentially, in terms of how it's derived, there really isn't one. So you have to memorize this. Base e exponential rule, derivative of e to the x is e to the x. One thing you do need to keep in mind here, though, is if I ask you to take the derivative of, let's say, e to the x squared, okay, this derivative is going to be equal to e to the x squared times the derivative. It's the chain rule is involved here. So then you have times 2x. So then if I wrote this aesthetically nicer, this would be 2x e to the x squared. Okay, so the chain rule is involved here. Okay, you don't see it here because what's the derivative of x? 1. Okay? Questions on either one of those? We're going to use some application here in a few minutes. Everybody good? All right, so now we're going to take a look at some inverse trig functions. So you guys dealt with these in pre-calc. If I asked you what's the inverse sine of 1/2, basically I'm asking you what the angle is. But when you're asked to take the derivative, here you have the derivative or the inverse sine of x is 1 over the square root of x squared. So remember, you have complementary functions. So when I take a look here, sine's complement is cosine. So you notice these derivatives are very similar. The only difference is this negative. Okay, so if this is the cosine, inverse cosine, the only difference is the negative. Okay, so just think about their complements. So take a look at the inverse tangent. The derivative of the inverse tangent is 1 over 1 plus x squared. Tangent's complement is cotangent. So here we have the inverse cotangent. The only difference is the negative. Okay, so it's just something to try to help you so you're not memorizing 1,000 different inverse trig functions.
One question, are we going to prove how...
Nope.
No, okay.
You can look at the BC videos if you want the proof, but I'm not making you prove them. These two and their complements are the most common inverse derivatives that you use. I'm not saying you will never see secant and cosecant. They're just not as common. Is it possible that on the AP classroom they're going to use them just because I'm telling you that they're not the common ones? Of course. Did I see any? Not in the practice that I did, but that's not to say that one won't ever come up. Homework, practice sheets, or whatever. But like I said, these 4 are the most common ones that you'll see. The inverse derivative, or the derivative of the inverse of secant, okay, is 1 over x times the square root of x squared minus 1, which is just another thing we have to remember. And then its complement is the inverse cosecant, and here we just have our negative. Okay, really, so what our interest is, other than your drill quiz, I'm interested more in how do you apply, how do you use these, and that's one of the most important things. A lot of us need to work through taking the derivative and practice taking the derivative, and part of that is because once we move into what we're using the derivative for, you're going to see these functions, and it's going to be expected that you know what these are. Just like when I, again, ask you the unit circle, it's expected that you know what it is. All right, so derivatives of exponential functions. So here we have our exponential base e, so that's what we're going to use. When we take the derivative here, our derivative, what's my, and I'm using this in quotes, what's my x term? Negative 5x squared. So when I take the derivative of this, it's e to the negative 5x squared, but then using the chain rule, this would be times what? Negative 10x. So if I didn't care what the aesthetics were, meaning I don't care what this looks like, I just care about my answer, am I done? Absolutely. Okay, but if we want it to look pretty, you've got, what, negative 10x e to the negative 5x squared, and you're done. I'm actually going to add a problem in here because I want you to see this. We don't have it on here, but we have the derivative. So this, let's say, take the derivative of the quantity of 5 to the x, x to the 5th power. Okay, first of all, what is this? What do I have to use here? I heard it a little bit louder. I do. I need to use the product rule. So I'm going to highlight what I would say this is my f, right? And then we'll pick something else for our g. Let me pick green. Okay, so this would be my g. All right, so here, when we've got our product rule, and that's why I wanted to add this in here because it includes our exponential function rule that is not base e, we're going to say f is equal to 5 to the x and g is equal to x to the 5th. Okay, and I also wanted to include the product rule because some of us are really struggling with when do we use this and how do we use this. So f prime, we're going to apply our new rule. So what is the derivative of this exponential? It's at the very top. It's number 17.
5 times 1.
5 times
x ln of 5.
Yeah, it's 5 to the x, natural log of 5. Okay, because this is my b. It's my base. My base is 5. Okay? And then g prime is 5x to the 4th power. Is that right? Okay, before I continue, is everybody okay with the derivatives? Again, unfortunately it's memorization and not all of us are good at that, but it's kind of what we would just have to know. All right, so now we need to use the product rule. So we have, I'll just call this f prime of x, meaning this whole derivative is equal to, so we've got f prime times g. So it doesn't really matter how I write this, right? So I've got x to the 5th power, and then we've got 5 to the x, ln of 5. So that's f prime times g. I just wrote this in front, plus f g prime. Can I combine these two? I have 5 to the x times 5x to the 4th power. Are they the same? This is 5 to the unknown power, right? And this is 5 to the 1st power times x of it, so they're not the same. So isn't this my derivative? I'm done. Okay, but I wanted you to see an application of this base right here. Okay, questions? Okay, let's take a look at B. Remember, this is just notation. Take the derivative with respect to x. Oh, what do I have to use here? Oh, yeah, I have to use a quotient rule. All right. So we've got f being equal to e to the negative x, and g is equal to the natural log of the quantity of 2x. All right. So what's f prime? Yeah, negative e to the negative x, because it's e to the negative x times the derivative of your exponent, which is negative 1. Okay? Ooh, g prime. This means we have to go back one section. What's the derivative of the natural log of x? 1 over, in this case, it's going to be 1 over 2x. And then I have to take the derivative of what's inside. So this derivative right here is 1 over 2x times 2. Is that true? Hmm?
Right, so it would be 2 over 2x, which would be 1 over x.
So can I write this as 1 over x? Yes. Okay. So now I'm all set up. We just need to put everything in, right?
Say 1 over 2x.
I beg your pardon?
Why did you say 1 over 2x?
Why is this 1 over 2x? Somebody. Yeah. It's the derivative rule for the natural log of x, but in this case our x term is 2x. That's right. So we put the whole thing in the bottom. So that actually was last section, which was 2 classes ago, right? Okay. So now this is f prime times g. So this would be negative e to the negative x times the natural log of the quantity of 2x minus fg prime. Isn't this right here? Can I write this as, because this is in the bottom and this would also be in the bottom, 1 over e to the x times x? Isn't that the same thing? and then this is all over g squared. So it is the natural log of the quantity of 2x, and this whole thing is squared. Okay, what's the problem with this problem? I have a what?
Denominator.
I have a denominator in the numerator, more simply known as a complex fraction. True? Yes. Okay, so how do I get rid of that? Multiply by what is my least common denominator? E to the x times x. So I'm going to multiply by x e to the x over x e to the x. So when I distribute here, this is essentially in the bottom, true? So what does that leave me with? I got a negative x times the natural log of 2x, right? Because these two cancel. So this is negative x ln of the quantity of 2x. Then here is just what? Minus 1? All over this big thing, right? So I've got x e to the x times the quantity of the natural log of 2x squared. That's my answer. You have to simplify your complex fractions. Okay, so for some of us, was this probably not enough space? Probably not. Yes, dear?
Could you take the log properties and make it ex?
You mean this one right here?
No, from the very beginning, make it e to the negative power of x minus.
No, because you're not taking the natural log of this. It would have to be, the natural log would have to be out here to do that.
Okay.
That's a good question. All right, do you guys remember the logarithmic differentiation? It was that last problem that I did on that last page of the last notes. There's a lot of lasts in there. In this case, if I asked you to take the derivative, the problem here is I've got a variable locked inside my exponent. And typically, the only way that I'm going to be able to get that out is to take the natural log, and then I can use my expansion rules. So here you have to use what's called logarithmic differentiation, which means I need to take the natural log of y is equal to the natural log of x cosine of x. Okay, so this helps me how? Yeah, this can jump down in front. So then what I have is the cosine of x times the natural log of x, which means when I take the derivative, what do I have to use? Product rule. So we have the natural log of y is equal to cosine of x, natural log of x, and then just to separate, I'll put this here. So now we can identify, we've got f is equal to the cosine of x, g is equal to the natural log of x. And this is so we can derive the right-hand side. Okay, so f prime is negative sine of x, is that true? What's g prime? A little bit louder? Yeah, 1 over x. Okay. So when I take the derivative of the natural log of y, what do I have to make sure that I put next to it? Yeah, dy dx. So we have 1 over y, dy dx is equal to, so this is f prime times g. So negative sine of x, natural log of x, and then times fg prime. So is this what, plus cosine of x over x? Okay. This is just going to require one, maybe 2 last steps. So tell me what I have to do to solve for dy dx, which is essentially the same thing as y prime. Multiply by y, but this is a unique case because do we know what y is equal to?
Yes.
We do. Look at your original problem. It's right here. So when I'm multiplying by y, essentially I'm multiplying by x to the cosine of x. So we have dy dx is equal to the quantity of negative sine of x, ln of x, plus cosine of x over x. And this whole thing is times my original problem, which is x to the cosine of x. It's very ugly, but it's the answer. Questions? You sure? Okay, if I were to derive C, what would I have to use? Yeah, definitely I have to use a chain rule. So what's the first part of my derivative? And in this case, it's with respect to t. It's because of variables t. It's not a big deal. What's the first part of my derivative? Okay, so we have the cosine of 3 to the t power. And then I need to take the derivative of 3 to the t power, which is going to make me go up to the top and use, what, rule 17? I don't expect you to know that number. I just have it in front of me. So what's the derivative of 3 to the t? Yep, 3 to the t times the natural log of 3. You're done, right? That's it. That's all I can do. Questions? Okay, does anyone have any questions on any of those problems that we just went over? Because now we're going to jump into the inverse, which again requires you to use a chain rule. Okay, for a lot of these. All right, so can someone tell me why we multiplied by x cosine of x? Yeah, so here, if you're solving for dy dx, you have to move this y over here. But we know what y is equal to. So I just saved myself a step. Instead of multiplying by y and rewriting all this messiness right here, I know that y is equal to x cosine of x. So I made the substitution. Okay, inverse trig functions. We want to find dy dx. So the derivative for the inverse sine of x is 1 over the square root of 1 minus x squared. But what is our x term? It's x squared. So we have to square x squared, true? That's my x term. And then what do I have to do? Yes, I need to take the derivative of x squared. So dy dx is equal to, all I'm doing right now is using the rule. So here we've got 1 over the square root of 1 minus x squared squared, which I know you can do in your head, I'm just writing it down, times the derivative of x squared, which is 2x. So essentially, my derivative is finished, true? But I could make it look a little bit nicer. This is equal to 2x over the square root of 1 minus x to the 4th power, and you're done. Can I simplify the denominator by saying it's 1 minus x squared? No, you cannot. It is the square root of a quantity. So you would have to know what x is first. This is not the same thing as the square root of 1 minus the square root of x to the 4th. Not the same. This is a difference of squares, but factoring it doesn't help me either. So just leave it. Everybody good with A? It's important that you understand that. Okay, cosine. All right, so dy dx. Okay, so this derivative is similar to the sine in the sense that it is 1 over the square root of 1 minus x squared. What's the only difference? It's negative. Okay, and I know that because I'm cheating and I'm looking at my rules at the top of my paper. Okay? I don't know them yet, right? Okay, so we're going to deal with this first. So this is going to be negative 1 over the square root of 1 minus the square root of x squared. That's going to get simplified in just a second, agree? Okay, then it's times, what's the derivative of the square root of x? 1 over 2 square root of x. Okay, if I was nervous, could I stop there? If it was free response? Absolutely. But if it's multiple choice, am I done? No. So I just need to combine. So I still have a negative 1 in the top, because nothing moves up. Can I simplify this? Yes. So this is 2, and you've got 2 different ways that you could look at this. This could be square root of x times the square root of 1 minus x. Is that true? Another way you might see this, because these are the same root, this would be under here. So another way you could see this is negative 1 over 2 times the square root, and then you have an x times a quantity of 1 minus x. Most of us would not make this leap, but I wanted to show you because if you had this type of problem on a multiple choice, this is how you would see it. Okay, but if you left it like this, that would be okay too, because we're probably going to use it to find what? Slope. Okay? Questions? How's everybody doing? You guys doing okay? I know we're still only on the first page. This is more the application. What we're about to talk about is like Algebra 1 concept in just a minute. So it won't be as bad, I promise. All right, this last one. Hot mess here because we're dealing with tangent. And this tangent is a fraction. Okay, so a couple different things. One thing that you need to think about, this is the same thing as the inverse tangent of x over 3 minus 1/3. All I did was make them into two separate fractions where this is one fraction, okay? And the reason why I did that is because we will have to use the chain rule here, and when I take the derivative of 1/3, what's the derivative going to be? 0. Does everyone see what I'm talking about? It's just going to be easier to see that that goes away, and then what's the derivative of this going to be? Yeah, it's just 1/3, because it's x times 1/3 or 1/3 x. Okay? Does that make sense? All right, so we're going to take the derivative. dy dx is equal to, so we're looking at the inverse tangent, and it is 1 over 1 plus our x squared. So we have 1 over 1 plus, and we have the quantity of x minus 1 over 3 squared. And then it's times, you guys already told me what this derivative is. What's this derivative on the inside for chain rule? Yeah, it's 1/3. Okay, this is a complex fraction, and I can guarantee you that if you do see it, it's going to be simplified. Okay, so let's kind of go through some of this so that we can see what happens. We still have a 1 in the top. We have this 3 in the bottom. And I'm going to simplify this right here. So it's 1 plus the quantity of x minus 1 squared, and my denominator is squared. So this is what, a 9? Can I distribute this 3? Yeah. So this is, I'm actually going to move up here to make sure I have enough room. 1 over 3 plus the quantity of x minus 1 squared, and this is over 3. Agree? Because these reduce when you distribute. Okay, so I have a complex fraction. How do I get rid of that? Don't get a common denominator. Get rid of your complex fraction. How do you get rid of it? Multiply by 3 over 3. Whatever your denominator is to get rid of, you want to multiply by that. So we're going to multiply by 3 over 3, which then is going to give me 3 in the numerator, 9 plus the quantity of x minus 1 squared. That's actually your answer, simplified. This is dy dx. I know some of you don't like it. It is what it is. I hate that thing. I hate that. Okay, questions on that derivative before we continue? Are you sure? I have a question. I'm going to go through this in a minute, but I have a lot of questions, but